Okay, well, I screwed up. We were supposed to have a test today, but I didn't mention it at all last week, so I figured let's move it to next Tuesday. But if anybody has, if that causes any problems for anyone, come talk to me and we can schedule a different time for you to take it. So exam 1 is going to be Tuesday, what would that be, the 7th? Yeah. And the topics are going to be everything up through rigid body, free body diagrams. So there aren't going to be any rigid body statics problems where you use the equations. You just have to know how to do the free body diagrams. And so everything we've been doing, I don't know, I think pretty much everything we did in the last class and everything we're going to do today is for problems that are not going to be on the test. Anybody have any homework questions? Okay, let's just keep going with what we're doing. So we did a couple of two-dimensional rigid body statics problems. I want to talk about this idea of equipolant systems. And the idea with equipolant systems is with rigid bodies, there are multiple combinations of loads that create the same behavior. That cause the same behavior. These combinations of loads are called equipolant systems. We've seen one example of this already. So we've already seen this with couples. Remember, a couple is really a pair of equal and opposite forces acting at a distance from each other. But the way we treat them is as if it's a pure moment. We don't deal with those forces at all because I showed with that quick little mathematical, derivation that the behavior of a rigid body subjected to two equal and opposite forces is exactly the same as the behavior of that body subjected to just a pure moment. Okay, and so that's how we treat it. So we treat a couple as a pure moment. Even though it's really equal and opposite forces. It's worth pointing out, I think, that this idea of equipolant systems only works with rigid bodies. If you have deformable bodies, like imagine a hunk of clay, or really in real life everything's deformable, but a lot of times it's reasonable to treat certain things as if they're rigid. But if you have a hunk of clay and you apply a couple to it, let me draw a picture of this. So this idea doesn't work with deformable bodies. So for example, say you have this hunk of clay and you apply a force here and a force here. What would happen is you'd get big local deformations at the places where you applied forces, right? And so the behavior would be different than, say, taking a screwdriver and applying a pure couple to the center of the thing, right? But with rigid bodies, the behavior will be exactly the same. There are a few different kinds of equipolant systems, and I'm not going to go into all the different ones. Sometimes it's useful to find a new representation of a set of loads. But the one I want to talk about is, let's see, the other one we'll use, besides the couples, is that any force can be moved along its line of action anywhere you want without changing the behavior. Bless you. You can move a force anywhere along its line of action without changing the behavior. So, for example, if this is the body and this body has a force applied like this, its line of action is the line parallel to that force that goes through where the force is really applied. So all of this is the line of action. And mathematically, you can put that force anywhere along this red dotted line without changing the problem. And there are times that that makes it easier. Notice that force doesn't even have to act on a material point on the body. You know, we could take this force F and say it's applied over here where the body doesn't even exist. It sounds weird, but mathematically everything will work out the same. So the force doesn't even have to act on an actual material point. Okay, so let me show you an example of where this is useful. So let's say this exercise enthusiast is, ooh, I'm making it look harder in this picture than on my notes. Okay, so he's holding on to like this roller thing, this little wheel that's pressed against the wall, and he's just standing there like that. That looks really hard. I'm glad I'm not doing that. It looks like Gru. And we want to know, what are the reactions? Okay, well, let's say this is what we know about it. We know that the height of the roller is 0.8 meters. And the center of mass of this person would probably be about here somewhere, probably off the material a little bit. Did you know the center of mass of a body could be off of the body? It makes sense if you think about like a ring or something. You know, the center of mass of a ring has to be right in the center where there's nothing there. But you know, high jumpers, they do the funny looking back thing, the Fosbury flop. You know, they run up, turn around sideways, and then jump over the bar backwards. The reason that works so well is because with the way their body is at every step when it's going over the bar, good high jumpers can get their whole body over the bar, never touch the bar, and yet their center of mass is never as high as the bar. That's pretty cool, isn't it? So yeah, like so like you're limited, your jumping ability limits how high you can get the center of mass of your body. But if you contort your body in the right way, you can get your whole body over it piece by piece, and at each moment the center of mass is below the bar. It's really cool. Okay, so let's say that it's 0.5 meters from the foot contact to here. And we're going to treat this like a friction contact. And this we're going to treat like a roller. Okay, so looking at this, it looks like we're missing a couple of important pieces of information. We don't know how high the center of mass is. We only know horizontally how far out it is. And we don't know horizontally how far out the roller reaches. We only know how high it is. So let's draw a free body diagram and see what's going on. It is a roller is one of the joint types that I listed. So it's a force perpendicular to the surface it's rolling on toward the chosen body. So the forces we have are the weight acting at the center of mass. Oh, I didn't give a mass. 80 kilograms. So 80 times 9.81 is 784.8. And then at the friction contact, we have an unknown force vector. I'll call that RA. And then the only other place there's contact with the outside world is at the roller. So that's perpendicular to the, there's the surface that the roller rolls on. It's perpendicular to that toward the chosen body, so I'll call that RB. And now the first question is, are we going to get enough equations to solve this? You should always ask yourself that after you draw the free body diagram. So this is a 2D problem. How many equations are we going to get from Newton's laws? 2 from Newton's second law, but then a third one from the rotational equation, from the moment equation. So 3 equations, and we have 1, 2, 3 variables. So far it's looking good. And now let's think about, let's fill out that table of rho, the force, and the moment. And I'm going to put the about point here. Okay. There's no reason you have to put it there. You can choose any point you want. But okay, so here's rho, force, and moment. And first, let's do the friction contact. That's acting at the about point. So what's the rho vector? 0. The force vector is RAX, RAY, and the cross product is 0. So I'm going to start writing, when I do 2-dimensional problems, I'm going to start writing it in shorthand like this. That's really the z component of the moment, you know, and this is really 0, 0, 0, RAX, RAY, 0. But the only non-zero component of a moment in 2D is the z component, so I'm just going to write that. Okay, the next force is the weight. So how are we going to come up with a rho vector for the for that weight force? We don't know the height of it, but since it's an equipolant system, if we put that force anywhere along this line, we can just say it's on the ground or say it's at 0, you know. Say it's at the same height as the about point, and then all we have is an x component of that rho vector. So the rho vector then is 0.50. The force vector is 0, negative 784.8. And if you take that cross product, 0.5 times negative 784.8, so multiply those, then subtract those multiplied together, and you get negative 392.4. That was given in the problem, that horizontal distance is 0.5. So I just moved, instead of treating the weight force like it was up above the ground, I just treated this weight force like it had the same y component as RA, and then that rho vector only has a horizontal component. And then RB, line of action is like this. So I'm going to move that to, I'm going to say the rho vector for this, you know, keep this going all the way. I'm going to say that the rho vector just has a vertical component of 0.8. So 0, positive 0.8. Force vector is negative RB, 0. So we have 0 times 0 minus 0.8 times negative RB. So positive 0.8 RB. because it's pointing in the negative x direction. Because a roller force is perpendicular to the surface and then toward the chosen body, toward the body you're isolating. So that's why we know it's to the left. Yep, right. So Newton's second law says add up all these and set them equal to 0. Rax, Ray plus 0, negative 784.8. Plus negative RB 0 is equal to zeros. And the moment equation says 0 minus 392.4 plus 0.8 RB is equal to 0. I don't have those. Can someone calculate these? So we know that from this one we can calculate RB. Okay, and it comes out positive 490.5. And then RA is equal to positive 784.8. And the x component is equal to RB, so that's 490.5. So there are some problems where it'll simplify your calculation to move the force along its line of action. By the way, we could have done that problem. It's not like this is the only way you could do it. You could just leave that height in as some unknown h and this distance in as some unknown width or something. And you would see when you went through the calculations that those just didn't come up in the equations. So it's not like we couldn't have done this problem without treating it as an equipolant system, but it did simplify the math a little. All right, so now we're going to go to talking about 3D problems. And the overall approach stays the same. What changes is, so overall approach is the same. But in 2D, Newton's second law gives two useful equations. And rotational Newton's second law, the moment equation, gives one useful equation. So the total is 3 equations that you get out of it. In 3D, Newton's second law gives 3 useful equations. The moment vector equation gives us 3 more equations. And so add those and you get 6 equations. If you do a problem in 2D, a single rigid body, you can solve for you can solve for 3 variables. If you do a rigid body problem in 3D, you can solve for 6 variables. Um, by the way, that might give you sort of the idea like, oh, well, let's just do, if we don't have enough equations for the number of variables in 2D, let's try doing it as a 3D problem. We get more equations. But it doesn't work like that because when we do a problem in 2D, we're already saying that the motion is all limited to 2 dimensions. And so if you do it as a 3D problem, motion is limited by forces that you have to apply and couples you have to apply out of the plane. And so anyways, it doesn't help to go from 2D to 3D. But in 3D, we are going to look for 6 variables and 6 equations. The main thing that's harder in 3 dimensions is representing the joints. Figuring out what kind of loads are applied by. Okay, so first let me do a problem, a 3D rigid body problem without joints, just like we did in 2D. We did a problem where I just gave all the loads and we solved for them. And then from there, I'll define some of the 3D joints you'll see, and we'll talk about like full statics problems. All right, so here's an example where we don't have to deal with the joints. Let's say there's a rectangular solid. The loads, there's one in this corner with a y component and a z component. And on the top, right in the middle of that edge, there's a force F. In the center of mass of this object, that's way in the middle, there's a force that's like a weight force of 588.6. On the top face, in the middle, there's a couple. And in 3D, this is how we're going to represent couples with the double arrows. I guess the double arrowheads is supposed to be like 2 forces of a couple. And so we have an x component of 100 Newton meters, and a y component of 300 Newton meters. And then in this corner, we have a full unknown force vector with an x component, a y component, and a z component. And I'll call that one B. That's the force B.
What is it? What are those feathers again? Feathers.
Oh, these, that just says that this, we're not talking about a force vector here, we're talking about a couple. So those are components of a moment vector, a pure moment vector. And I have to give the dimensions. Let's say the height is 0.5 meters. And that's also the depth. And then let's say the length is 1 meter. And we want to calculate the unknown loads. Okay, so is there any way to look at this and tell whether this is going to be solvable or not? There isn't exactly a way, but there is something you should do to make sure that it's plausible that you could solve this. Remember, when you isolate this, when you use Newton's second law and the rotational equation, you're going to get at most 6 good equations out of this. You're going to get 6 equations. It's possible some will be redundant or linear multiples of each other. So the most you can get is 6 good equations. And so if you have more than 6 variables that you're solving for, you know you can't do it. So first thing is just count up the variables. We have 2 components of a force here, a third variable here, this force, and then 3 force components here, so 6 variables. So we're solving for 6 variables with, at most, 6 equations. So it looks promising. Looks good so far. And so now I'm just going to write out this table. And we're going to choose an about point and just go through and calculate the row vector, write down the force and the moment vector, and then put them into the equations. Is there any place that occurs as a better place than others as an about point? Yeah, B. I mentioned a few minutes ago, it usually simplifies the math a little bit if you put your about point where you have the most unknown forces. We have 3 components of an unknown force at B, so let's put the about point there. And I'll start with that one. So if the about point is at B, what's the row vector for that force B? 0. And this is 3D now, so I have to include all those components. The force is Bx, By, Bz. And that cross product gives you 0 moment. And then let's go to the weight. Okay, so think in order of, these 3D pictures can get a little overwhelming trying to figure out what that is. But just think of going in what direction you have to go and how far parallel to the x component, parallel to the y component, and parallel to the z component. Let me draw the coordinate system I'm using. So this is the direction of the coordinate axes I'm using. Okay, so to get from the about point to the center of mass, how far do I have to go in the x direction? Half meter in the negative x direction. And then I have to go, well, how far in the y direction? Quarter of a meter up. And then how far in the z direction? Yeah, quarter of a meter in the negative z direction. So negative 0.5, positive 0.25, negative 0.25. And that force vector that's applied there is 0, negative 588.6, 0. And you get a moment vector of negative 147.15, 0, 294.3. So you see here that now we're doing 3-dimensional problems. It's the first time that we've seen those moments have components besides just the z component. Okay. In general, now we can have any of those components non-zero. And then next, let's go up to this force F. So that's right, just like in 2D. Yep, we don't care about the O vector or the force vector. You just put those in for the moment. For the force F, going from the about point, how far do we have to go in the x direction? Yep, negative 0.5. How far in the y direction? 0.5 and z direction? 0. We're going from here all the way to the top. This F is on the top of that. Yeah. So negative 0.5, positive 0.5, 0. And that force vector, F is in the positive z direction. So the force vector is 0, 0, F. And that cross product is positive 0.5 F, positive 0.5 F. And next is the couple. Just like in 2D with the couple, we can cross those out. We're not going to use those. And we're just going to put in the values 100. We have 100 Newton meters in the positive x direction, 300 Newton meters in the positive y direction, nothing in the z direction. So that's just 100, 300, 0. Yes.
Negative,
Okay. Because, so in the x direction, did you learn cross product with the determinant way of thinking about it? Okay, so if we write this as I, J, K, and we're taking the cross product of negative 0.5, 0.25, negative 0.25, and the second one is 0, negative 588.6, 0. That's 0.25 times 0 minus negative 588.6 times 0.25. And I don't know, does that come out to negative 147? Okay. It is negative 0.5x, positive 0.25y, negative 0.25z. Sure. And anybody who has a TI-89 calculator or an Inspire, you can actually enter all of these as variables, and it'll do the cross product for you and leave it as variables. It's sort of a nice feature. I don't think it works on the 84 or the 83, maybe the 86. I'm not sure about that. But anyways. Try it with a different letter. I don't know if X, Y, and Z might be reserved, but try it with A, B, and C or something. You have to do it with variables also that you haven't already put values into. You know what I mean? Oh, okay, sure. Let's look at it after. What did you get? You got 0 for x? Okay, well, let's talk about that after too. Something went wrong there. I know it's not 0 for x. Okay, so now that we have this, we can go to Newton's second law and add up all the things in the fourth column, set them equal to 0. So bx, by, bz plus 0, negative 588.6, 0, plus 0, 0, f is equal to zeros. And then the moment equation says zeros plus negative 147.15, 0, 294.3 plus 5f, 0.5f, 0 plus 100, 300, 0 is equal to zeros. And now we have a system of 6 equations for 6 variables, which can be a pain to solve by hand, but easy to solve with reduced row echelon form. So let me just set up this matrix. So we have 6 equations. That means we're going to need 6 rows, and we're going to need 7 columns, 1 for each variable, and then the constant. Oh, that'll get a lot bigger. Yeah. Okay, so this is equation 1, 2, 3, 4, 5, 6. And the variables, you can do them in whatever order. I'll go bx, by, bz, f, ay, az. And then this is the constants. And you have to remember to move the constants over to the right side of the equation, or else all the answers are going to be backwards. So the first equation says, well, bx is equal to 0. We don't really have to solve for that. That just tells us bx is equal to 0, but I'm just going to put it in here. So 1 times bx is equal to 0, and all the rest are zeros. I'm only going to put in the non-zero coefficients. The second equation says by is equal to 588.6. So 1 by is equal to positive 588.6. Not really any reason to solve that one either, but I'm going to do it. The third one says bz plus f is equal to 0. So bz times 1 plus f times 1 is equal to 0. And then the fourth equation says 0.5f is equal to, combine those two, and you get positive 47.15 on the right side. So 47.15 is equal to 0.5f. Okay, there's not really any reason to solve for that one either. We could have, so sometimes you can get away with solving these by hand if a lot of them are, just give you the value like that. The fifth equation, 0.5f is equal to 300. Is that right? Yeah, negative 300. Oh, no, I didn't. Sorry, I didn't finish this. That's why that looks weird. I forgot to do AY and AZ. So we have to do one more. Sorry about that. So what's the row vector for this A force? In the x direction, how far do you have to go? -1, and then nothing else. So that's just going to be -1, 0, 0. The force vector, we have no x, and then we have AY and AZ. And if you take that cross product, you get 0, AZ, -AY. Okay. So sorry about the mess here, but I'm just going to squeeze this into the equations I already have written. So for Newton's second law, we're also adding on the vector 0, AY, AZ is equal to zeros. And for the moment equation, we're also adding on the vector 0, AZ, -AY is equal to zeros. Okay, so the first equation doesn't change. The second equation, we also have 1 times AY. The third equation, we also have 1 times AZ. The fourth equation, we had right. The fifth equation, we also have 1 times AZ. Oh, and I haven't filled that out yet. So we have 0.5F plus 1 AZ is equal to -300. And then the last one says -AY is equal to 294.3. Any questions about that?
Yeah.
Negative. Thank you. And so then if you solve that with reduced row echelon form, you get the B force vector is equal to 0, 294.3, 252.85. The force F is equal to 94.3. These are both newtons. And the force A has no x component. Y component is 294.3. And the z component is -347.15.
So that F, you don't write it in component form.
Well, it depends. If I ask for the force vector applied there, then you do have to put it in component form, and then all you do is you take this value that we solved for and plug it back into the force vector here in Newton's second law. So it would just be 0, 0, 94.3. Okay.
Could you write it like that?
Sure, yeah. Any other questions? Okay, so now we have to talk about 3D joints. So now, an object starts out with more degrees of freedom than it did in 2 dimensions. But remember, if something's moving in the plane, the degrees of freedom that it has are 2 translational ones, this way, and a rotational degree of freedom. Okay. So there were 3 that we started with, and then the joints were categorized by which of those they limited. There could be a joint that allowed rotation, but it fixed the location of this point. And so that had a force in this direction, a force in this direction, but no couple. And we're going to think about it the same way in 3D. The loads applied by a joint are going to be determined by what degrees of freedom are restricted by the joint. Okay, but before you connect a body to a joint in 3D, how many degrees of freedom does it have? 6. Yep, that's exactly right. So now you have this can move this way, or this way. So that's the 3 translational degrees of freedom. And now the thing that's sort of new to think about is it still has this rotational degree of freedom, but now it has 2 more that didn't exist in 2D. It can do this, and it can do this. Okay? So those are the 6 degrees of freedom. And to think about what loads a joint applies, you just have to think through all of those 6 and think, what does that joint keep this from doing? Okay. We'll go through categories the same way I did with 2D joints. We're going to start with joints that introduce a single variable, just like we did with 2D joints. What was the most variables introduced by a 2D joint? Well, if every variable limits 1 degree of freedom, there's only 3 degrees of freedom available, so 3 is the most there can be. Yeah, and so in 3D, we're going to start with joints that introduce a single variable, just like we did in 2D, but we're going to go all the way up to joints that limit all 6 degrees of freedom, which again is going to be a fixed joint. Okay, so we're just going to go through those one by one. Okay, so first, joint category 1. The joints in this category apply force with a known direction. And so they only introduce 1 variable into the equation. The first one of these is a frictionless contact. And that works just the same way it did in 2 dimensions. If this is body 1 and this is body 2, a free body diagram of body 1 like that, and a free body diagram of body 2 looks like the second one is what I'm going to call a roller, but this time In 2 dimensions, you could think of a roller as like a wheel, but a wheel has a preferred direction. You know, a wheel will let you roll freely in line with the way it rolls, the way it spins, but it won't let you slide back and forth, right? And so a roller in 3D you want to think about as like a ball. Well, we don't have that kind of chair here, but yeah, you want to think about it as a ball that can roll in any direction. So, question? What? Yes, right. Ballpoint pen. Yeah, mouse ball. Yes, both. Yes. So a ball, not a wheel. So that would look like this. There's body 1, there's body 2. So a free body diagram of 1 looks like that. And of 2, it looks like that. For both of these, joints, the value of R can only be positive because the ground in neither of these cases can it pull down on the object. So R must be positive. If you get through a calculation and R is negative, either you made a mistake or there's something wrong with that problem definition. Okay, next is joint category 2. So this applies 2 components of a force. Which brings 2 variables into the equations. And there's only one of these. And that's a wheel with a preferred direction. Okay, so this wheel rolls along a line like that. And I'm going to choose my axis directions to be X along that path of motion, Y up, and Z perpendicular. So a free body diagram. Okay, so let's think about what degrees of freedom are restricted here. This can roll freely along the x-axis. So there's no force applied along the x-axis. It isn't free to slide along the z-axis, and it isn't free to sink into the floor. So there are components of force in the z direction and the y direction. Okay. Now let's think about rotations. Is this thing prevented from tipping over by that joint? No. So there's no couple about the z direction. Is it prevented from tipping over side to side? Well, it sort of depends how fat the wheel is, I suppose, but we're going to treat it like it's free to tip. That thing isn't providing any stability. And so no couple about the x direction. And then we're also going to say that it doesn't restrict it from rotating like this. So there's no component of couple, and there are two components of force. So I'm going to write this as a force component, Fy, and a force component, Fz. Yep. Any questions about that one?
There's always only one FC component. It's never. There's only one FC, right?
Yes.
Only one force in the z direction.
Right. Okay, so now joint category 3. This introduces 3 force components. And so that's 3 variables. And there's only one in this category. That's a ball and socket joint. That looks something like this. So let me show you a 3D printed one of these. Okay. So here's a 3D printed ball and socket joint. You can see, can you tell what's going on there? So this allows rotation about this axis, rotation about this axis, rotation about this axis, I like swiveling it. So no couples are applied. But if you think about the point at the center of the ball, it doesn't allow any translation in any direction. The location of that ball stays where it is. Okay, so that means that this joint applies 3 components of force, but no components of couple. Okay, this is like your hip joint or shoulder joint. Okay, so free body diagram. Let me call this body 1 and this body 2. Free body diagram of body 1. Looks like this. And then a free body diagram of body 2 by Newton's third law, a cup. Looks like this. And actually, if write this with that double subscript notation, you can think of this one as F on 1 by 2, and this one as F on 2 by 1, or negative F1, 2. Any questions about that one?
In some cases, you draw two free body diagrams and you call both of them R. This one you do negative R.
Okay, yes. That's because it's the difference between a force where you know the direction and a force where you don't know the direction. On these other ones, like on these, I knew that the direction of that force was up. And so then Newton's third law, you just switch the direction of the arrow and keep the same variable. But if you don't know the direction of the force, you draw just the axis directions and use the, that subscript version of Newton's third law. Okay. Okay, next is joint category 4. So this is a joint that introduces 4 variables. And the one type of joint in this category is a pin joint without thrust. So let me show you what that means. So think of this joint as a single pin joint. Okay, it's a pin joint because there's this long pin here that connects through whatever it's attached to and lets it rotate freely about that pin. Okay, that's what a pin joint does. This one doesn't prevent it from sliding side to side along that axis. Okay, S is the force that would keep it from sliding side to side. So this is one without thrust. Okay, it can freely translate like that. So let's think about what degrees of freedom are restricted by this. It can translate this way, so there's no force there, but it can't translate. I can't pull out with this hand. And so I can't do that like this, and I can't do it up and down. Okay, so there are 2 force components that are applied to the piece I'm holding here by the joint. Okay, you see that? I didn't explain that super well, but you can't pull it like this, parallel to the table. You can't pull it up, vertical to the table. You can slide it like this. So there's 2 components of force and one without one degree of freedom that's not restricted. And then for rotations, you can do this, So there's no couple there. But I can't rotate this here, can you see what I'm trying to do? I can't rotate it that way. And I also can't twist it like a screwdriver. Okay, so there are two couples applied that limit rotation and two forces applied that limit translation. Now, this is where things get a little confusing. Let me draw a pin joint without thrust. Here's the pin. And we have one body there and another body there. And I'm going to choose the coordinate axes with the z-axis along the pin and the x-axis that way and the y-axis that way. Okay, so a free body diagram looks like this. There's no force along the z-axis, but there is along the x-axis and the y-axis. So there's a force in the x direction and a force in the y direction. And then those rotations, ones that are restricted, are about the x-axis. So there's a couple component mx and a couple component my. And here's the thing that's unusual about this that we haven't seen yet. The couples, so notice, the couples mx and my are only included if they're needed for equilibrium. And the reason that we do it like that is because a pin joint can resist rotations about those two axes, but it doesn't do it very well. And usually you don't want to rely on a pin joint to resist rotations. If you are going to think about how to break this joint, you wanted to wreck this thing, what would you try to do? You wouldn't probably try to pull it apart this way or this way. The most efficient way to break it would be to try to bend it like that or to try to twist it, right? It just isn't very good at resisting those rotations. And so in some cases, these joints are relied on to prevent rotation. But in cases where they're not relied on to prevent rotation, we treat it like it doesn't do it at all. Okay. Any questions about that? Okay, well, let's stop there and I'll finish next time. So we just finished the joint with 4 variables. How many more categories do we have left? Two more. Yep.